Hello everyone, we will continue with our discussion on steam power plant, and I like to take up an example for steam power cycle with regenerative feed heating. For simplicity, we will take the example of regenerative feed heating with an open feed water heater. And the problem is given in this slide. A steam power plant operates on an ideal regenerative Rankine cycle with a single open feed water heater. The turbine inlet conditions are 10 megapascal, 650 degree Celsius, and the condenser pressure is 10 kilopascal. If bleeding takes place at 2 megapascal, determine the fraction of total flow through the turbine, that is blade, and the thermal efficiency. Both the problem, let me acknowledge, both the problems, the previous problem and the present problem are taken from the book Thermodynamics and an Interactive Approach by Subroto Bhattacharya, and the publisher is Pearson 2015. If we go to the cycle diagram is given here, and we have used the same state points, whatever numbers we are showing here, the same numbers are used in the problem itself. If we go to the state point, we see at point 1 we have got pressure and temperature given. So, from there we can calculate the enthalpy. Then state 2, there is ideal Rankine cycle we have considered. So, the expansion up to state 2, up to which the entire amount of steam flows through the turbine. So, this is an adiabatic reversible adiabatic process. So, S 2 will be equal to S 1. So, as this state at point 1 is known, here we can calculate enthalpy, which will be needed for further calculation, and we can also calculate the entropy. The same entropy value will be there at state point 2. So, from there pressure is also given. So, we will be knowing, we know the condition of steam completely. So, we will be able to calculate its enthalpy. And then we can move to state point 3. In state point 3, that is the entry to the condenser. In the entry to the condenser, we know the pressure condition of the condenser. So, P 3 is known, and again S 3 is equal to S 1, because we are following a reversible adiabatic expansion process. So, we know the enthalpy. So, enthalpy at point 1, point 2 and point 3 are known. That means, along the expansion line, if you refer the cycle diagram which I have shown earlier. So, along the expansion line of the turbine, we know all the enthalpy values at different points. And then we move to point number 4. What is point number 4? If we now let us go back once to the cycle diagram. So, conditions were given here, we could calculate the enthalpy. This entropy and this entropy is same, and the pressure is known. So, we can calculate the enthalpy over here also. This condenser pressure is given. So, what we can do, we can equate the entropy of point 1 and point 3, and pressure is known. So, this enthalpy also we can calculate, and this state point is completely known. So, then from point 3 we can move to point 4, where it is saturated liquid, and we can calculate the enthalpy at this saturated liquid condition. So, that is also known. Then what we can do, the way I have I have told that pump work can be calculated. We can calculate the pump work and we can determine 0.5. Enthalpy at 0.5 we can determine. So, let us go back to the table of solution. So, at 0.5 this is the condenser pressure P2, P5 is known and then S5, let me see which is 0.5, let me see once again. So, 0.5 that you see it has been equated with 0.2. This is one important thing, that if this has to go to the open feed water heater, then the pressure at which we are extracting the steam, the condensate should be also raised to the same pressure, otherwise it will not go here. So, this pressure is known, this pressure is equal to P2. So, then in the pump P1 we raise the pressure from 0.4 to 0.5 and then it goes to the mixing chamber. So, pressure 5 is equal to the pressure at 0.2. Then we will be able to calculate the pump work and enthalpy at 0.5. That is what we have done. P5 is equal to P2. This is an adiabatic, reversible adiabatic process, and the similar way as I have described for the previous problem, we can calculate the change in enthalpy due to pump work, and ultimately we get H5 is equal to H4 plus the enthalpy change due to pump work, that is what, and then we will be able to calculate the enthalpy at 0.5. 0.6, where is the point? Where is this point? Let us see. So, 0.6 is the point at the exit of the open feed water heater. So, now we will do some sort of an energy balance for the feed water heater, which I have also written earlier, that steam with enthalpy at 0.2 is entering the open feed water heater, condensate with enthalpy at 0.5 is entering the open feed water heater, and from the feed water heater liquid water at saturated liquid condition and at a condition 6, that is going out. So, now we can make an energy balance. The energy balance already I have written. So, same kind of energy balance we can use, and ultimately what we will get? We will get the condition of 0.6. X is equal to 0, that means it will be at the saturated liquid condition, and pressure will be the pressure of the extracted steam or bleed steam. Then we will get that enthalpy, that is 908.8 kilojoule per kg. Then again we have used another pump P2. So, P2 we have used, and then for P2 the inlet pressure will be P6 or the pump 2. So, inlet pressure will be P6 and outlet pressure will be equal to the boiler pressure. P7 is nothing but the boiler pressure. So, this will be the boiler pressure. Again we can assume the compression process in the pump is a reversible adiabatic process. So, by adding this pump work we can calculate the enthalpy at H7. So, now you see, if we go back, now you see that from 0.7 there is this much of heating will be done in the boiler itself. This is the economizer part of the boiler. The economizer part of the boiler that has been reduced, and then there will be evaporation and superheating. So, amount of heat that will be given in the boiler, that is equal to H1 minus H7, that will give us the heat transferred to the working fluid in the boiler from the fuel. All right. So, P7 then we have got and the enthalpy we have got. Next table we can go, or next calculation we can go. Here from energy balance, as I have explained earlier, we can get that R, which is the ratio of these two mass flow rates, that is equal to 0.239. That means, this much amount of this is the ratio. That means, if the total mass flow rate we know, multiplied by this quantity will give us how much steam we are extracting, all right. And then we can find out the thermal efficiency. So, thermal efficiency can be calculated by a different method. We can simply do eta thermal is equal to W turbine minus W pump divided by your Q boiler, because that is the amount of thermal energy we are taking from the, that is the amount of thermal energy we are taking from the boiler. So, eta thermal is equal to W T minus W P pump by Q boiler, and this W T has got two part. From 1 to 2, W T from 1 to 2, entire amount of steam has expanded, and then plus W T from 2 to 3. If we see the cycle diagram, this will be again clear that we have taken two work done. This is m dot 1 amount of mass is expanding from 1 to 2. So, there will be this enthalpy difference multiplied by your m dot 1. So, we can write, let me write the next step first, m dot 1 into H 1 minus H 2 plus we can write m dot 3 multiplied by H 2 minus H 3. So, this we can write. So, this is the turbine work. Then there are two pump work. So, W P 1 plus W P 2. We have shown it by Roman number. So, then W P 1 by W P 2. There are two pumps P 1 and P 2. So, we can show that. And then boiler work, you can show, you can see that boiler work it is from 7 to 1. So, we can write Q boiler is equal to H 1 minus H 7, H 1 minus H 7. You see all these quantities we have calculated. So, we can calculate the thermal efficiency, but there is another doing it also. What we can do, that thermal efficiency is equal to 1 minus Q dot out by Q dot in, and Q dot out, this is your Q dot out. Q dot out, what is the heat transfer in the condenser, and this is the heat transfer in the boiler. So, this is your Q dot in. So, this is also one way of calculating the efficiency, and we will have 45.19% of efficiency. So, efficiency will increase, there is a definite increase in efficiency if we go for feed water heating. It would be a good exercise if we do exercise, it would be a good exercise that do not consider any feed water heating. So, you assume that entire steam, the entire mass of steam is expanding through the turbine, and this pump is raising the pressure from P 4 or P 3 up to P 1 or P 7, and then you do the cycle calculation and see what efficiency you get. So, obviously, the efficiency in the first case when there is regenerative feed heating, we will get higher efficiency, but as I have told, the work output will be lower. So, with this I have explained the working of Rankine cycle and the modification of Rankine cycle I have explained, and the efficiency also I have efficiency of the Rankine cycle, how the efficiency changes with feed water heating, that I have explained. Now, I like to discuss a few additional points in connection with this. That is number and position of feed water heaters. So, this is one thing I like to discuss. As I have told, in an utility power plant, that means in a power plant which is generating electricity, large power plant, there will be number of feed water heater. So, now obviously, the question is where we have to place the feed water heater. How we know that at that particular where means at what pressure we should extract steam. First thing is that feed water heater increases, addition of feed water heater increases the efficiency. But if we see that what incremental increase in efficiency we get by addition of the first feed water heater, the incremental increase in efficiency by the addition of the next feed water heater is less. So, I can write, this is important, the incremental increase in eta thermal by the addition of feed water heater decreases. So, this is a very important concept. The incremental increase in eta thermal by the addition of feed water heater increases, decreases, sorry. So, if it is so, when we are adding feed water heater, we are having additional pipeline, we are having additional pumps maybe, and also we are having additional equipment like feed water heater. So, with all these things, the complexity of the pump plant that increases. There will be, whenever there is addition of pipeline, addition of some sort of an equipment, pump, losses are also increasing. So, what we are getting? We are getting a diminishing increase in efficiency and rather increase in the losses and some amount of irreversibility. So, we have to stop somewhere. So, we cannot go on increasing the feed water heater infinitely. So, that is one message I like to give you, that there is a limitation depending on the plant size and depending on the operating condition of the plant, of the cycle, we have to select the number of feed water heater. But 6, 7, 8 number of feed water heaters are not uncommon in case of a large steam power plant. So, those many feed water heaters are used. Of course, it will depend, as I have told, it will depend on the size of the plant, and it will also depend on the operating condition. That means, the pressure at which steam is supplied to the first stage of the turbine. So, that is regarding the number. So, let us say somehow we have decided the number, then how do I determine the placement of the feed water heater, or rather how do I determine the extraction point from the turbine. Extraction point means this is a turbine, high pressure steam is coming over here from boiler, here ultimately it is going to condenser, and let us say we have got extraction point 1, I am denoting as E 1, I have got E 2, I have got E n, n number of extraction point I am having. Corresponding to the pressure P 1, P 2 and P n, in between I have got other extraction points. So, how should I decide regarding P 1, P 2, P n etcetera for a good plant design? So, without going into derivation, this can be derived, but without going into derivation, let me explain how it is done or how ideally it could be done. Let us say this is my steam power cycle and this side is T and this side is S. Schematically, this is showing the cycle and there are different, let us say I am showing it only for open feed water heater, just for the sake of understanding it. So, you see the steam is to be heated from this condition, sorry, the condensate has to be heated from this condition to this condition, and out of this much of heating of condensate is coming from the boiler. This is the heat transfer from the boiler, and the rest of it is coming from feed water heater. And let us say I have got n feed water heater, n numbers of feed water heater. So, what I have to do, let us say the condensate is coming at some temperature T and then I have to raise it to the temperature at which steam generation is there at the boiler pressure. So, corresponding to the boiler pressure, I know the saturation temperature also. So, let us say I have to raise delta T amount of delta T, the temperature rise of the condensate. So, by an approximate analysis, it can be shown that delta T by n plus 1, if, so let us say this is the quantity called x. So, this x amount of temperature rise will be there or should be there by each of the feed water heater. By each of the feed water heater, if I raise the temperature of the condensate by an amount x, where x is given by delta T divided by n plus 1. So, then what is happening? Delta T is equal to n plus 1 into x, and if delta T total temperature rise for the condensate n into x is the temperature rise of the condensate by n number of feed water heaters, each raises the temperature by x, and then x amount of temperature rise is there by the economizer. So, basically what we have done, we have, by introducing feed water heater, we have reduced the heat requirement from the economizer. Now, we have decided that we will use n number of feed water heater. Each of the feed water heater will raise x amount of each of the feed water heater will give x degree of temperature rise, and then economizer will also give x degree of temperature rise. So, assuming this as a thumb rule, one can determine the pressures at which steam can be extracted. So, the end points from where the steam will be extracted, by using this thumb rule, one can determine that pressure. So, this will give, generally this gives a good design and good energy utilization, and that is what is also followed, of course, keeping in consideration other plant constraints. So, this is generally followed in steam power plant or steam power cycle design. With this, we come to an end of our discussion regarding the regenerative feed heating cycle. So, this is very important because all the practical cycle will have regenerative feed heating, and regenerative feed heating is also a good example how we can utilize the energy in a better manner. So, with this we try to end this discussion, and the next discussion we will take up a few more points regarding steam power plant, and then we will move to other power cycle. Thank you.